Okay, looking at number 5 on page 150. This one involves a trampolinist called John who is doing a somersault. They give us some information, his mass, his height, and they tell us to model John as a solid rod of 1.8 meters, and therefore we can use the rotational inertia equation I, capital I, equals 1 over 12 times the mass times h squared, where h is the length of the rod, in this case John's height. Then going to part A, calculate John's rotational inertia. That is exactly the equation we're going to use. I equals 1/12 mh squared. So you can see here in the solution I've just plugged the numbers straight into that equation. 75 is his mass times 1.8 squared, which is his height, divided by 12. So we're taking a 12th of that figure, and you get 20.25 kilograms meters squared for the rotational inertia in that case. Okay, B, explain the assumption concerning the centre of mass that is made when the model is used to calculate John's rotational inertia. Of course, the main assumption is that his centre of mass is exactly in the middle of his body length, the 1.8 meters, and that he rotates about this point. In actual fact, this will not be perfectly true. A human body is not, the same as a uniform metal rod. That's fairly obvious, I suppose. Okay, part C. Show that John's total kinetic energy is 2,300 joules. Now, to find this figure, we need to add all the linear motion and the kinetic energy that results from the linear motion to the rotational motion and the rotational kinetic energy that results. So here we have the working. This is the linear formula, and next to it we have the rotational kinetic energy formula involving rotational inertia I and the rotational velocity, or the angular speed, omega. If you calculate the linear kinetic energy, you get this figure, and you calculate the rotational using the information given in the question, 4.1 for radians per second for the angular speed and 7.5 for the linear speed. Add them together and you get this figure here, 2,300 joules, rounded to two significant figures. And finally, part D. You can see part D on this video anyway. The angular momentum, L, is what we're asked to calculate. So now that we've got the rotational inertia of John from part A, we use the unrounded figure, of course, calculate that. It rounds to 83 to two figures, kilograms meters per second for the unit of angular momentum.